Okay, so business algebra, we're starting chapter 4 this week, which is exponential functions and logarithms, which we will get to later. But we're starting with exponential functions. Before we do that, let's define what a rational exponential expression is. If we have a raised to the m over n power, so if you have a fractional exponent, and a is a number, m is an integer, and the denominator has to be positive, and then a to the m over n power is really the nth root of a raised to the m power. So when you have something like, for example, 4 to the 3 halves here, this is really the square root of 4 raised to the 3rd power. Now we can actually evaluate that because the square root of 4 is 2. 2 cubed is 8. Now it's true you can also do the square root of 4 cubed. 4 cubed is 64. The square root of 64 is also 8. Generally, though, it's easier to make the numbers smaller before they get bigger instead of doing the opposite. For other numbers, it would be less practical to do it this way. So I would stick to this way. It's generally easier. This way could be harder depending on what's happening. So 27 to the 1/3 power really means the cube root of 27, which is 3. So negative exponents, 64 to the negative 3 halves is the same as 1 over 64 to the positive 3 halves, which is 1 over the square root of 64 cubed, or 1 over 8 cubed, which is 1 over 512. This is an example of how the numbers, it would be much harder to cube 64 and then to take the square root of it than to go down to 8. Even 8 cubed is relatively large, but 64 cubed is pretty massive. So we have properties for exponents, and here's some definitions of the rules and how it's helpful. So a to the x power is a unique real number for all real numbers x. All that really says is the function f of x equals a to the x, where a is our constant base besides 1, has a domain of negative infinity to infinity. A to the b power equals a to the c, if and only if b equals c. It has a special property called 1-to-1 for functions. What that means is it's both a function, every input has exactly one output. Furthermore, every output is exactly one input. If our base is bigger than 1, and m is less than n, then a to the m is less than a to the n. Basically, what they're saying is if you take a number like 2 and you raise it to a power, the 2 to a larger power is bigger than 2 to a smaller power, simply because 2 keeps doubling the number. However, if our number is a fraction, it's the opposite. If you keep multiplying by a half, your number is actually getting smaller. So if a is between 0 and 1, and m is less than n, then a to the m is actually bigger than a to the n. 1/2 squared is bigger than 1/2 cubed, because 1/4 is bigger than 1/8. So we can use these to solve some problems, or at least simplify. Before that, let's talk about what they look like. So we have a few options here. It says either a is greater than 1, or a is between 0 and 1. Now we can also have a negative exponent or a positive. So 2 to the x, if you just make a table, 2 to the 0th power is 1. Anything to the 0th power is 1. 2 to the 1st power is 2. 2 squared is 4. 2 cubed is 8. So on the right side, it kind of looks a little bit like a parabola. So let's talk about what 2 to the negative 1st power is. It's really 1 over 2 to the 1st power, which is 1/2. 2 to the negative 2nd is 1/4. 2 to the negative 3rd is 1/8. So on the left side, we have 1/2, 1/4, 1/8. Instead of going up like a parabola, it levels off. So we kind of have our behavior like an end behavior situation with rationals on the left side, but behavior like a quadratic on the right side. Now the only difference between this and 1/2 to the x is if you make your table, remember multiplying by a half, 1/2 to the 0th power is still 1. 1/2 to the 1st is 1/2. 1/2 squared is 1/4. Cubed is 1/8. So instead of it flattening out on the left side, it's now going to flatten out on the right side. So it's similar to what just happened, except it goes up on the left, much like 2 to the x goes up on the right. Now what happens if our exponent is negative? 2 to the negative x. This is what we call horizontal reflection. So it takes the 2 to the x and it flips everything. So instead of going up on the right and leveling off on the left, it's now going up on the left, leveling off on the right. You may notice that this looks exactly like what we just did. Furthermore, if I do a reflection of 1/2 to the negative x, I get what looks like the original, 2 to the x. Now why is that? We only really look like we have 2 pictures here. So is that the case? Well, let's talk about 2 to the negative x. That's equal to 1 over 2 to the x power, because that's what we do with negative exponents, which is the same as 1/2 to the x. So yes, they are actually the same thing. So there's only really 2 ways this can look. Either it looks a little bit like a quadratic on one side and levels off. It really just depends which side is which. Now, if you want to move an exponent left or right, you add a number to the exponent. So basically, how does 2 to the x compare to 2 to the x minus 1? This one is right 1. It moves the whole function. Right 1 compared to 2 to the x. If you want to move an exponential up or down, you add numbers to the end. So 2 to the x versus 2 to the x plus 1. This one is up 1 from 2 to the x. So our translations will work like other function translations do. Okay, so let's look at some basic problems here. Solving exponential equations, given points. Substitute a value in, find the a, and replace it to get your function. So find the function of the form f of x equals a to the x that passes through the given points. We've got the point 3, 125. So that means f of 3 equals 125, which means 125 has got to be equal to a to the 3rd power, because that's what goes in for x in this equation. Take the cube root to get rid of the cubed. You get a equals 5. So this function is actually 5 to the x power. We'll do one more. Let's do 3. So f of x equals a to the x. F of 5 equals a to the 5th, and we know that that's 1 over 243. We take the 5th root. We get 1 over, what was the 5th root of 243? It is 3. So a is 1/3, which means our original function is f of x equals 1/3 to the x power. Let's do the word problem underneath this. The exponential growth of a deer population in the country can be calculated using the model t equals 60,000 times 1 plus 0.07 to the n, where 60,000 is the current population and 0.07 is the growth rate. Predict the population of the deer in 4 years. This is a fancy way of saying plug in 4 for n, 60,000 times 1.07 to the 4th. From here, you would have to use a calculator or even type it into Google. So let's see what we get when we do that. 60,000 times 1.07 to the 4th is 78,647.76. Now, let's be realistic here. You can't really have 0.76 of a deer, so I would always round this to the nearest whole number. So 78,648 deer. And we'll continue this section in the next video.